Welcome! In this video, we'll tackle LeetCode problem number 17, letter combinations of a phone number. This problem is a classic example of leveraging recursion and backtracking to generate all possible combinations based on a given input. Let's dive in and explore the solution step by step. In this problem, we are tasked with generating all possible letter combinations that can be represented by a string of digits, where the digits range from 2 to 9. This mapping of digits to letters is based on the layout of a traditional telephone keypad. For example, the digit 2 maps to the letters of B and C, while the digit 3 maps to D, E, and F. It's important to note that the digit 1 does not correspond to any letters, and we can ignore it in this problem. The input will be a string of digits, and our goal is to produce a list of strings where each string is a valid combination of letters derived from the input digits. The order of the combinations in the output list does not matter, so we are only concerned with generating all valid possibilities. For example, if the input string is 23 foot, we need to determine the possible letter combinations. The digit 2 corresponds to of B and C, while the digit 3 corresponds to D, E, and F. To form the output, we combine each letter from the first digit with each letter from the second digit. This results in the combinations, add A, AF, BD, B, BF, CD, C, and CF. These combinations are listed in the output as a collection of strings. On the other hand, if the input string is empty, there are no digits to process, so the output is simply an empty list. This highlights an important edge case where an empty input directly leads to no combinations. Now, consider another example where the input string is 7. The digit 7 maps to the letters P, Q, R, and S on a telephone keypad. Since there is only one digit in the input, the output will consist of these letters as individual strings. Therefore, the output is P, Q, R, S. Along with these examples, the problem comes with a few constraints. The input string can have a length between 0 and 4, which means we'll never have to handle more than 4 digits. Each character in the input string is guaranteed to be a digit between 2 and 9. These constraints ensure that the problem remains manageable and well-defined. To summarize the key edge cases and constraints, if the input string is empty, the output should be an empty list since there are no digits to process. If the input contains only one digit, the output will simply be the corresponding letters for that digit as individual strings. Additionally, because the maximum length of the input string is 4, the largest possible output list will contain 81 combinations. This happens in the scenario where all 4 digits map to 3 letters each. These constraints and edge cases give us a clear framework for solving the problem efficiently. To solve the problem of generating all possible letter combinations from a phone number, we begin by considering a few approaches. First, there's the brute force method. The idea here is straightforward. For each digit in the input, you simply append all the letters associated with that digit to every existing combination. While this approach might seem simple and easy to implement, it quickly becomes inefficient as the input grows. This is because the number of combinations increases exponentially with the number of digits, leading to a time complexity of 4 to the power of n. For example, with just a few digits, the number of combinations can skyrocket, making this method impractical for larger inputs. So, while it's a valid approach, it's not one we'd recommend due to its inefficiency and inability to scale. A much better option is to use recursive backtracking. This approach is both optimal and elegant. The idea is to dynamically generate combinations by exploring all possible paths one step at a time. Starting with an empty string, we iterate through the digits, and for each digit, we recursively append each letter to the current combination. This allows us to systematically explore all potential letter paths without generating unnecessary combinations. The time complexity here remains 4 to the power of n, which is the minimum work required since we must generate all combinations. However, the space complexity is reduced to n, as we only use the recursion stack up to a depth of the input size. This method is concise, efficient, and avoids redundant computation by ensuring each path is explored only once. There's also an iterative approach using a queue, where we start with an empty string in the queue and iteratively build combinations. While this avoids recursion, it requires additional memory to store intermediate results in the queue, making it less intuitive and less space efficient than backtracking. Given the strengths of recursive backtracking, it stands out as the optimal strategy for solving this problem. It's intuitive and minimizes redundant computation while handling the exponential growth of combinations efficiently. The key insight here is to recognize that each digit corresponds to a branching point in a tree of possible combinations. Backtracking allows us to explore this tree dynamically, appending letters as we go, rather than pre-computing all combinations up front. This approach not only saves memory but also aligns naturally with problems that involve combinations or permutations. By treating each recursion depth as a level in the tree, we can systematically generate results while maintaining a compact space footprint with the recursion stack. While the iterative queue method eliminates recursion, it requires significantly more memory to store intermediate combinations. And brute force, as discussed earlier, is not feasible for larger inputs due to its inefficiency. In summary, recursive backtracking provides a balanced solution, offering a clean and scalable approach to tackling this problem effectively, both in terms of time and space complexity. This problem, letter combinations of a phone number, asks us to generate all possible letter combinations for a given string of digits, where each digit corresponds to a set of letters on a traditional phone keypad. For instance, the digit 2 maps to the letters of B and C, while 3 maps to D, E, and F. However, the digits 0 and 1 do not map to any letters. The first step in our algorithm is input validation. If the input string is empty, we can immediately return an empty list because no combinations are possible. Next, we create a mapping of digits to letters using a dictionary for quick access. This dictionary will store each digit as a key paired with its corresponding list of letters. For example, 2 maps to B, C, 3 maps to D, E, F, and so on. This mapping is essential for efficiently translating digits into their respective letter sets as we generate combinations. Using this dictionary structure ensures constant time access to retrieve the letters for any given digit. Now, we employ a recursive backtracking approach to systematically generate all possible combinations. The recursive function takes 2 parameters, the current combination, which is being constructed, and the remaining digits. If there are no remaining digits, we add the current combination to the result list and stop further recursion. For the first digit in the remaining digits, we retrieve its corresponding letters from the dictionary and iterate through them. For each letter, we append it to the current combination and call the function recursively with the updated combination and the remaining digits. This allows us to explore all possible paths. The recursion stops when there are no more digits left to process, which forms the base case. Additionally, the algorithm handles edge cases, such as when the input string is empty or includes invalid digits like 0 or 1. In terms of complexity, the time complexity is 4 to the power of n, where n is the number of digits, as each digit can map to up to 4 letters. Generating and storing these combinations also requires 4 to the power of n time. The space complexity of the algorithm is n, where n is the length of the input string, due to the space used by the recursion stack. Now, let's break down some key insights into how the algorithm works. First, recursive backtracking systematically explores every possible letter combination for each digit, ensuring that no combination is missed. Backtracking is particularly useful because it allows us to undo choices and explore alternative paths efficiently. Second, using a pre-computed dictionary for digit-to-letter mapping provides quick access and avoids unnecessary recomputation. Lastly, the algorithm explores one level deeper for each digit, ensuring the combinations are generated in a structured and predictable manner. In terms of data structures, the dictionary stores the digit-to-letter mapping, a list is used to store the resulting combinations, and the call stack is implicitly used to track the current state of the combination being formed during recursion. The call stack plays a crucial role in tracking the current state as we recursively build combinations. Now, let's look at the Python implementation of this algorithm. We define a function, letter_combinations, which takes a string of digits as input and returns a list of all possible combinations. If the input string is empty, we immediately return an empty list. We then define the digit-to-letters dictionary to map each digit to its corresponding letters. Inside the function, we define a helper function called backtrack for the recursive process. The backtrack function takes 2 parameters, the current index of the digit being processed and the current combination being built. The base case for the recursion is when the length of the current combination equals the length of the input string. At this point, the combination is complete, and we add it to the result list. Otherwise, we retrieve the letters corresponding to the current digit and iterate through them. For each letter mapped to the current digit, we append it to the current combination and recursively call backtrack with the next index. After the recursive call, we use the backtracking technique to undo the choice by removing the last letter from the combination. This ensures that we can explore all possible paths without affecting other branches of the recursion. We initialize an empty list, combinations, to store the final results and start the recursion by calling backtrack with an index of 0 and an empty combination. Once the recursion has explored all possible paths, the combinations list contains all the valid letter combinations, which is then returned as the output. To better understand how this works, let's walk through an example with the input 23. Initially, the combination is empty. The digit 2 maps to A, B, C, so we iterate through each letter. For each letter from 2, we append a letter from 3, which maps to D, E, F. This process generates combinations like AD, AE, and AF. After completing these, we backtrack and explore the next letter from 2, such as B, and pair it with all letters from 3, generating BD, B, and BF. Finally, we repeat the process for C, generating CD, C, and CF. The final output is a list of all these combinations: AD, A, AF, BD, B, BF, CD, C, CF. This illustrates how the algorithm efficiently explores all possible paths while systematically backtracking to ensure no combination is missed. Here, we start by defining a class called solution and a method named letter combinations that takes a string of digits as input. The first thing we handle is an edge case. If the input string is empty, we immediately return an empty list since there are no combinations to generate. Next, we define a dictionary called phone_map that maps each digit from 2 to 9 to its corresponding letters on a phone keypad. For example, 2 maps to ABC, 3 to DEF, and so on. This mapping is crucial as it forms the basis for generating the letter combinations. After that, we define a helper function called backtrack which uses recursion to explore all possible combinations. The function takes two parameters: index, which keeps track of the current digit we're processing, and path, which is a list to build the current combination. Inside backtrack, the first condition checks if the index has reached the length of the input digits. If it has, it means we've formed a complete combination, so we join the letters in path into a string and add it to the combinations list. If not, we retrieve the letters corresponding to the current digit using phone_map and store them in possible underscore letters. At this point, we need to explore all the letters and possible underscore letters for the current digit. Using a for loop, we iterate through each letter. For each iteration, we add the current letter to the path list, representing a choice. Then, we call the backtrack function recursively, moving to the next digit by incrementing the index. After the recursive call, we undo the previous choice by removing the last letter from path, which allows us to backtrack and explore other possible combinations. Finally, we define an empty list called combinations to store all the valid combinations we generate. To start the recursive process, we call backtrack with an initial index of 0 and an empty path. Once the recursion completes, the combinations list will contain all the possible letter combinations, which we then return as the result. Here, we start by importing the necessary Java utilities and defining the solution class. In the method letter combinations, we handle an important edge case first. If the input string digits is null or empty, we immediately return an empty list. This ensures that our program can gracefully handle invalid or empty input without proceeding further. Next, we define a mapping of digits to their corresponding letters based on a standard phone keypad. For example, the digit 2 maps to ABC, 3 maps to DEF, and so on. This mapping is stored in an immutable map for quick access. We then declare a list called combinations to store the resulting letter combinations. To generate these combinations, we use a recursive backtracking approach. The backtracking function is called initially with a starting index of 0, an empty string builder to build the combinations, the input string digits, the phone map, and the combinations list. This sets up the foundation for generating all possible letter combinations. The method then returns the combinations list after all recursive calls are completed. Now, let's look at the backtracking function itself. The function takes several parameters, including the current index, the path being built, the input digits, the phone map, and the combinations list. The first check inside the function ensures that if the current index matches the length of the input digits, it means we've built a complete combination. At this point, the current path is converted to a string and added to the combinations list. If not, the process continues. We retrieve the digit at the current index and use the phone map to get the corresponding string of possible letters. For each letter in this string, we append the letter to the path, recursively call the backtracking function to handle the next index, and then remove the last letter from the path to backtrack. This ensures that all possible combinations are explored by systematically trying each option and reverting changes when backtracking. To solve the problem of finding all possible letter combinations for the input digits, we start by initializing a few key components. The input here is the string 23-foot, which corresponds to the digits on a phone keypad. We use a mapping called phone_map to associate each digit with its possible letters. For example, 2 maps to ABC and 3 maps to def. We'll also initialize an empty list called combinations to store the final results. The process begins with a recursive function called backtracking, starting at index 0 and with an empty path, which will store the current combination being explored. For the first recursive call, the digit at index 0 is 2, which means we have the letters A, B, and C to explore. Each of these letters will be added to the path one at a time. For example, we add it to the path, making it A, and then proceed to the next digit by recursing with index 1. Similarly, we try paths 4, B, and C, each time moving to the next step in the recursion. Now, in the second recursive call, let's consider the path where we've added A, so the path is currently A. The next digit in the input is 3, which maps to the letters D, E, and F. Each of these letters will now be appended to the path, creating combinations like A, D, A, E, and A, F. For each of these new paths, we recurse further with index 2. At this point, the index equals the length of the input digits, which means we've completed a valid combination. For example, the path A, D forms the combination add, which is added to the combinations list. After adding the combination, we backtrack by removing the last letter, returning to the path A, and repeat the process for the remaining letters E and F. Once all paths starting with A are explored, we backtrack to an empty path and proceed with paths starting from B and C, following the same recursive steps. By the end of this process, the combinations list contains all possible outcomes: add A, AF, BD, B, BF, CD, C, CF. When the input is a single digit, such as 7, the process is much simpler. Here, the digit 7 maps to the letters P, Q, R, and S. Since there's only one digit, we don't need to combine it with other digits. Instead, we directly explore each letter. Adding P to the path immediately forms a valid combination, as there are no more digits to process. The same happens for Q, R, and S. Each letter is added to the path, recognized as a complete combination, and added to the combinations list. The backtracking process ensures we reset the path after each letter is processed. Since there's only one digit, the final output consists of just these letters, P, Q, R, S. Now, let's consider an edge case where the input string is empty, meaning there are no digits to process. In this scenario, we handle the case up front by checking if the input is empty. If it is, we can immediately return an empty list, as there are no possible combinations. This avoids unnecessary computation and ensures the function handles edge cases properly. From this, we can observe a few important aspects of the solution. The function relies on recursive backtracking to explore all possible letter combinations. Temporary results are stored in a path, which is updated using append and pop operations. The base case of the recursion ensures that once we've processed all digits, the current combination is finalized and added to the results. Finally, the efficiency of the algorithm depends on the number of digits in the input, with a worst-case complexity of 4 raised to the power of the number of digits. To better understand the solution, let's visualize the data structures involved. The recursive stack is a key component, as it keeps track of the current digit being processed and the corresponding path at each step. This stack grows and shrinks dynamically as we explore different combinations in Backtrack. Alongside this, we maintain the combinations list, which stores all the completed letter combinations. From a complexity perspective, the time complexity of the solution is O, 4 to the power of n, where n is the length of the input digits. This is because each digit can contribute up to 4 letters, leading to an exponential number of combinations. The space complexity is O, n, which accounts for the maximum depth of the recursion stack. Together, these data structures and their characteristics provide a clear picture of how the solution efficiently generates all possible letter combinations. To analyze the time complexity of this solution, we start by understanding the number of recursive calls. Each digit in the input string maps to a specific set of letters. For instance, 2 maps to ABC, 3 maps to def, and so on. Most digits correspond to 3 letters, but 7 and 9 map to 4 letters each. In the worst case, assuming every digit maps to 4 letters, the total number of possible letter combinations is 4 raised to the power of n, where n is the length of the input string. Additionally, within each recursive call, we iterate through the letters for the current digit and construct the combination by joining the letters in the path list. This operation takes linear time, or O, n, since the length of the path is proportional to the input size. Combining these factors, the overall time complexity becomes O, 4 to the power of n asterisk n. When we consider the total work done by the algorithm, it is a combination of the number of possible combinations and the work required to construct each combination. As mentioned, there are 4 to the power of n combinations in the worst case, and each combination requires O, n, work. This gives us a total time complexity of O, 4 to the power of n asterisk n. Now, if the input string is empty, no recursive calls are made, and the best case time complexity is O, 1. However, in the average or worst case, where all digits are valid and mapped to 3 or 4 letters, the time complexity remains O, 4 to the power of n asterisk n. This reflects the dominance of the exponential growth in the number of combinations as the length of the input string increases. The space complexity of the solution is determined by the maximum depth of the recursion stack, which corresponds to the length of the input string. Since we process 1 digit per recursive call, the recursion stack can grow to a depth of n, resulting in O, n, space usage. Additionally, during recursion, we use a path list to store the current combination being formed. This list also has a size proportional to the input length, contributing another O, n, to the space complexity. The combinations list, which stores the final output, is not considered part of the auxiliary space since it represents the result of the function. Lastly, the phone_map dictionary is a fixed-size data structure with constant space usage since it only contains mappings for digits 2 through 9. Overall, the space complexity is dominated by the recursion stack and the path list, leading to O, n. With the recursion stack and the path list contributing to the auxiliary space complexity, the total auxiliary space usage is O, n. Now, let's compare this backtracking approach with a brute force method. In a brute force approach, we would generate all possible combinations of letters for the input digits up front and then filter out invalid ones. This method has a complexity of O, 4 to the power of n asterisk n, for generating combinations, plus additional overhead for filtering. In contrast, the backtracking approach is more efficient because it generates only valid combinations by exploring one letter at a time and backtracking whenever necessary. This allows it to avoid unnecessary work and minimize memory overhead. By building combinations incrementally and pruning invalid paths early, backtracking achieves the same O, 4 to the power of n asterisk n, complexity but optimizes the work done per combination. To summarize the mathematical justification for the time and space complexity, we know that the total number of combinations in the worst case is 4 to the power of n, assuming all digits map to 4 letters. For each combination, constructing the final string requires O, n, work. This results in an overall time complexity of O, 4 to the power of n asterisk n. On the space side, the recursion depth and the path list each contribute O, n, making the total space complexity O, n. These calculations confirm that the backtracking approach efficiently handles the problem within the constraints of this complexity. When working on this problem, there are a few common mistakes to watch out for. One of the most frequent errors is neglecting to handle edge cases properly. For example, if the input string is empty, such as when digits equals an empty string, failing to return an empty list as specified in the problem can result in errors. Another mistake is incorrectly mapping digits to their corresponding letters. For instance, if you map the digit 7 to PQRS but miss the letter S, your solution won't produce the correct output. It's critical to double-check the problem description to ensure your mappings are accurate. Additionally, using mutable data structures like lists during recursive calls can lead to subtle bugs if their state isn't reset correctly. Instead of modifying the original list, consider creating a new list for each recursive path, for example, by using path plus char. Lastly, inefficient base case handling can cause unnecessary computations. Make sure to terminate the recursion as soon as the combination length matches the input digits to optimize your solution. Now, while recursion is often the most intuitive way to solve this problem, it's important to note that it can lead to Stack Overflow errors for very large inputs. Iterative approaches can help you avoid this issue, but they require careful management of states between iterations. From an interview perspective, this problem is a classic test of recursion and backtracking. What interviewers are looking for is your ability to structure a clear recursive solution while avoiding common pitfalls like unhandled edge cases or poor state management. It's also useful to recognize the pattern here. This is a combination generation problem, and similar patterns appear in problems involving permutations, subsets, or generating valid expressions. Be ready to discuss the trade-offs between recursive and iterative approaches. While both can work, iterative solutions often use less memory for larger inputs. Finally, always highlight edge cases during an interview. Examples include an empty string, a single digit, or repeated digits, as these demonstrate a thorough understanding of the problem. This problem is also closely related to several others on LeetCode, which can help reinforce your understanding of backtracking and combination generation techniques. For instance, LeetCode problem number 39, combination sum, challenges you to generate combinations that sum to a target value, which also involves backtracking. Then there's LeetCode number 46, permutations, which focuses on generating all permutations of a list. Another great example is LeetCode number 22, generate parentheses, where the goal is to produce valid combinations of parentheses using a similar recursive structure. Lastly, LeetCode number 784, letter case permutation, extends the backtracking concept by generating variations of a string with different letter cases. Practicing these related problems can help you build a deeper intuition for recursive and backtracking solutions. There are several approaches to solving this problem, each with its own trade-offs. The most intuitive method is recursive backtracking, where you explore all possible combinations by recursively adding letters for each digit. While this approach is simple to implement, it uses 4 to the power of n memory for the recursion stack, where n is the length of the input. This can lead to stack overflow for very large inputs. Alternatively, you could use an iterative breadth-first search approach, which involves a queue to build combinations step by step. Starting with an empty string in the queue, you add letters for each digit iteratively. This avoids recursion but requires careful management of the queue and can be less intuitive to implement. Finally, Python's itertools.product function offers a concise way to compute the Cartesian product of the letters corresponding to the digits. However, this method doesn't demonstrate your algorithmic thinking and may be less suitable for interviews, especially if the use of libraries is restricted. Each approach has its strengths, so choose based on the problem's constraints and the context in which you're solving it. Great job! To summarize, we used backtracking to generate all possible letter combinations from a phone number. This approach highlights the importance of recursion and combinatorial logic in problem solving. Thank you for watching, and be sure to stay tuned for more coding tutorials. Keep practicing and happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!